the right questions in Stormwater Review. Here's what this program will cover: who we are, why we're here, the basics, the history of stormwater management, why an intervention is needed, what's changed, and what municipalities need to know. You can expect the complete program to be about 45 minutes in duration. The material in this program has been divided into 3 general sections. Part 1 is the introduction to stormwater management. Part 2 will cover regulations and best practices. And in Part 3, we'll introduce some compliance resources. Let's begin Part 1, Introduction to Stormwater Management. This program is intended to help you determine if an applicant developer is in compliance with the New Jersey Stormwater Management Regulations, so you can be comfortable approving or rejecting the applicant's plan. The approval of an applicant or developer's stormwater management plan lies solely with the municipality. Since 2004, municipalities have been required under their Municipal Stormwater General Permit to enforce statewide basic requirements for post-construction stormwater management in new development and redevelopment. The Municipal General Stormwater Permit also requires municipalities to do a number of other things, such as properly operate and maintain publicly owned stormwater facilities like gutters, storm drains, and outfalls, provide public education about stormwater issues, and adopt and enforce a number of stormwater-related ordinances. The additional requirements of the Municipal General Stormwater Permit are not the subject of this training program. Let's talk about what happens when it rains. It is absorbed by the plants, it infiltrates into soils, it evaporates, and it runs off impervious surfaces such as rooftops and pavement. This water that runs off is called stormwater runoff. Stormwater runoff must be managed to avoid flooding and polluted waterways. Stormwater is water from rain or melting snows that can become runoff, flowing over the ground surface and returning to lakes and streams. Let's look at the impact of municipal development on stormwater runoff. Runoff is low, about 10% in undeveloped areas, but more development creates more impervious surfaces, which leads to more stormwater runoff. In highly developed areas, this might mean 55% of rainfall becomes runoff, which needs to be managed. Let's talk about impervious cover. Roads, rooftops, parking lots, and other hard surfaces do not allow stormwater to soak into the ground. Those surfaces are called impervious. Impervious surfaces provide a surface for the accumulation of pollutants, result in increased polluted runoff and flooding, and inhibit the recharge of groundwater. Impervious surfaces also result in increased non-point source pollutants, increased runoff volumes, increased stormwater runoff rates, and reduced groundwater recharge. The hydrologic cycle, also known as the water cycle, also changes due to urbanization. When areas become populated, there is an increase in impervious surfaces. This results in much less infiltration and much more runoff. Engineers and other scientists are familiar with a graph called a hydrograph. A hydrograph is a visual tool to represent stormwater volume. A hydrograph plots stormwater runoff flows against time. The area under the line represents stormwater volume. Stormwater runs off slowly in a natural or undeveloped watershed, which yields a low peak and low volume. Stormwater runs off a developed area much quicker, yielding a higher peak and larger runoff volumes. So not only are we receiving more runoff, it is coming at us a lot more quickly. Let's take a look at the evolution stormwater management has gone through in recent years. Before the mid-1970s, the practice was to capture all runoff, send it through a pipe, and directly to the river. The problem here is that it caused downstream municipalities to get flooded. Then, from the mid-1970s through 2004, detention basins were the preferred solution to capture runoff, detain it, release it slowly to the river. The idea was to hold the water and let it out slowly, reducing the flooding impact that earlier approaches caused. Detain peak flow during large storm events, reduce downstream flooding during major storms, and use concrete low-flow channels to minimize erosion, reduce standing water, and quickly discharge low flows. But this system has limitations too. Basins are not well suited to managing runoff from smaller storms, as they directly discharge the stormwater runoff to nearby streams, waterways, or municipal storm sewer systems. Additionally, water is leaving the area and not being recharged or returned to the ground as clean water because these systems tend not to infiltrate. The limitations of the prior two programs prompted the development of the 2004 New Jersey Stormwater Regulations. These are often referred to as the new stormwater management rules, though they are over 10 years old. The regulations have two elements of particular relevance. The Municipal Stormwater Regulation Program requires all municipalities and large public complexes to obtain permits for their storm sewer system. The stormwater management rules set goals for new developments. These regulations address all three important aspects of stormwater management. Proper stormwater management reduces the impact of peak flows. Recharge is the infiltration that moves below the root zone to the groundwater table. These regulations require both removal of 80% of sediment and the provision of nutrient removal to the maximum extent feasible before the water leaves the property. The New Jersey regulations require a different approach to stormwater management. This video provides examples of better ways to manage stormwater, ways that are in accordance with New Jersey regulations.
Landscape architects design ways to divert and collect rainwater to prevent damage and replenish the aquifer. An aquifer is a below-ground natural reservoir of water that we use for drinking, cooking, bathing, and irrigation. The animation will demonstrate how rainwater is managed on a university campus plaza. The plaza surfaces are composed of standard materials. Concrete defines the walks and steps, and sod and lawn make up the open space. The building's roof, which also collects and discharges water, is a plain solid surface. Storm sewer and drains are ready to catch and pipe water away from the site and prevent flooding. During heavy rainfall, these materials, like concrete and sod, can only absorb so much water. The excess rainwater on the surface is funneled into the storm sewers. The building's roof diverts most of its water down pipes into storm drains as well. All this excess water, called runoff, can overtax and cause the storm drains to back up. This causes water to collect in ever-expanding pools. Too much runoff due to heavy rains can cause damage and sometimes catastrophic floods. It also results in more polluted, untreated water entering the aquifer. There are more effective means to manage stormwater using sustainable systems and materials that prevent flooding and replenish the aquifer. The first system is a green roof placed on top of a building. The green roof is layered with drainage materials, compost or planting soils, and vegetation. The green roof can absorb some of the rainfall, reducing the amount of water flowing into the storm drains. Another system involves porous pavement. Concrete surfaces are replaced with individual concrete bricks called pavers. Each paver is interlocked with its neighbor and separated by permeable material. The permeable material is composed of small crushed rocks, also called aggregates. Zooming into the cross-section, we see the permeable aggregates between and below the pavers. The aggregate-filled space acts as a sponge, absorbing water downward, diverting a good amount of runoff from the storm drains. The diverted water will eventually make its way into the aquifer below ground. The third system is called bioretention and is also known as a rain garden. A rain garden is a swale or channel that absorbs, holds, and slowly releases excess water. A rain garden section is composed of compacted soils defining the depth, width, and slope of the swale, sand and drainage materials, plant soils, and vegetation native to the region. Rain gardens are not only aesthetically pleasing, they also restore wildlife habitat. Now when it rains, water does not collect into large pools. Instead, our three systems absorb and redirect the excess runoff. The green roof prevents a lot of water from entering the storm system or hitting the ground. The porous concrete pavers absorb some of the rainwater and direct it downward into the aquifer. And the rain garden accumulates the remainder of the rainwater, preventing flooding and damage. As part of its function, the rain garden slowly releases rainwater into the aquifer over a 24-hour period. Just as important, the vegetation acts as a natural water purifier, absorbing pollutants and toxins from the water. Water is in high demand and shortages are common. These three systems are able to capture and treat more water than typical stormwater mechanisms. The systems are effective, easy to implement, and contribute to a more sustainable water management practice.
This concludes Part 1 of our program, Introduction to Stormwater Management. So let's move on to Part 2. The 2004 Stormwater Management Regulations address 4 objectives. Use non-structural management strategies. Protect communities from the impact of new development. Maintain groundwater recharge volumes. And protect waterways from pollution carried in stormwater runoff. Click on each topic to learn more. We'll discuss several specific non-structural strategies later in this program. New development can cause increases in stormwater volume and peak flows. It's important to retain water in the area to ensure groundwater recharge rates. Stormwater runoff can cause waterways to become polluted. The New Jersey Stormwater Management Rules apply to any major development, which includes a project disturbing 1 or more acres or increasing impervious surfaces by 1/4 acre or more. Remember, the term major development may also be defined differently in your local ordinance. Design and performance standards are established in the Stormwater Management Rules. 5 elements comprise the standards contained in the NJAC regulations. The requirements for the first element in the regulations, non-structural stormwater management strategies, include: plan the project using low-impact development or LID principles. Collect, infiltrate, and where possible, reuse stormwater near its source. Capture runoff from small storm events in vegetated systems to protect water quality and promote recharge. Minimize and disconnect impervious surfaces. The second element in the regulations is stormwater quantity. The requirements include post-development hydrographs for 2, 10, and 100-year events may not exceed pre-development hydrographs, or hydrograph peaks must not increase, and that any increase in volume or change in timing won't increase flood damage downstream. Or design measures so that post-construction peak runoff rates for the 2, 10, and 100-year storm events are 50, 75, and 80% of the pre-construction peak runoff rates. The next element is groundwater recharge. The requirements indicate: maintain 100% of average groundwater pre-construction recharge volume, or ensure infiltration increase post-construction for the 2-year storm peak volume. Next in the regulations is the element stormwater quality. Design best management practices, or BMPs, to reduce post-construction loads of total suspended solids of stormwater runoff. Install BMPs to provide nutrient removal to the maximum extent feasible. Click the information button for examples of interventions. In some areas, it might be necessary to combine interventions to achieve the standard of at least 80%. The final element is stormwater maintenance plan. All BMPs must have a maintenance plan. The plan must be comprehensive and must identify a responsible party. The bottom line is this: What are an applicant's objectives for achieving compliance? First, use non-structural strategies. Next, focus on systems that address water quality and groundwater recharge. Third, design systems that reduce peak stormwater runoff rates and meet water quantity requirements. The resources in this program will give you some guidance to the 3 general requirement areas. Non-structural strategies are used to provide one or more of these objectives: maintain groundwater recharge on the site, reduce sediment and nutrient runoff from the site, reduce the peak storm runoff rates from the site. Using non-structural strategies means not relying on pipes, catch basins, or engineered solutions. They include both environmentally sensitive site design and source controls that prevent pollutants from being placed on the site or from being exposed to stormwater. In order to achieve the 3 standards in the previous slide, we'll discuss 9 different non-structural strategies recommended to applicant developers. But first, let's explore the 4 categories they fall into: vegetation and landscaping, minimizing site disturbance, impervious area management, and time of concentration modifications. Using vegetation and landscaping involves preservation of natural areas, forested areas, riparian corridors, and high recharge areas, native ground cover, limiting turf grass areas, and vegetative filters and buffers, protecting them or planting new ones. Minimizing site disturbance means fit the development into the terrain, minimize clearing and grading, minimize soil compaction, and build on low permeability soil areas, excluding wetlands and transition zones. Impervious area management includes minimizing street widths and sidewalks, limiting parking and driveway areas, using pervious paving materials, disconnect impervious materials from draining directly into waterways, and installing vegetated roofs. Time of concentration modification means slowing runoff by surface roughness changes, slope reduction, vegetated conveyances, and limiting parking and driveway areas. Now that we have seen the 4 different categories, let's discuss further the 9 different non-structural strategies that are outlined in the stormwater management rules. Protect areas that provide water quality benefits or areas particularly susceptible to erosion and sediment loss. Minimize impervious surfaces and break up or disconnect the flow of runoff over impervious surfaces. Protect areas that provide water quality benefits or areas particularly susceptible to erosion and sediment loss. Minimize the decrease in the time of concentration from pre-construction to post-construction. Minimize land disturbance, including clearing and grading. Minimize soil compaction. Provide low-maintenance landscaping that encourages retention and planting of native vegetation and minimizes the use of lawns, fertilizers, and pesticides. Provide vegetated open channel conveyance systems discharging into and through stable vegetated areas. Provide other source controls to prevent or minimize the use or exposure of pollutants at the site, to prevent or minimize the release of those pollutants into stormwater runoff. Here is the first of the 9 types of non-structural strategies. Protect areas that provide water quality benefits or areas particularly susceptible to erosion and sediment loss, such as vegetative buffers. Note in this photograph, the downspout is carrying the water through an underground pipe directly to a storm sewer. A better solution would be to allow the downspout to discharge the rooftop flow over the pervious lawn. So strategy number 2 would be minimize impervious surfaces and break up or disconnect the flow of runoff over impervious surfaces. Let's look at 2 scenarios in an identical area with a total drainage area of 3 acres. 1 acre has directly connected impervious cover, while the adjacent 2 acres is pervious cover. We know that 90% of storms deliver a 1.25-inch storm. In the first scenario, the runoff flows directly to the stormwater inlet, causing over 28,000 gallons of runoff. But by simply pitching the pavement toward the grass first, then to the outlet, the result is a huge 85% reduction in impact. Let's check the data. Let's review that again. In a typical storm delivering 1.25 inches of rain, a typical connected impervious system generates 28,500 gallons of runoff. Once the impervious area is disconnected from flowing directly into the storm sewer system, runoff is reduced by 85%. Disconnecting impervious surfaces from flowing directly to local waterways can be as easy as redirecting a downspout to discharge over a pervious area. Another way to manage stormwater is to change impervious surfaces into pervious surfaces. This picture demonstrates pervious asphalt, where water passes through the surface into a stone storage reservoir below the porous asphalt surface. Number 5 of the 7 non-structural strategies is to minimize land disturbance, including clearing and grading. Here we see examples of preserving and not preserving natural lands. Number 7. Provide low-maintenance landscaping that encourages retention and planting of native vegetation and minimizes the use of lawns, fertilizers, and pesticides. How many of these images display positive strategies for low-maintenance landscaping? In addition to reducing the elements of a landscape that interfere with proper stormwater management, such as minimizing the use of fertilizers and pesticides, shade trees and shrubs are a low-maintenance solution. Provide vegetated open-channel conveyance systems discharging into and through stable vegetated areas to slow water movement. This simple checklist of the 9 non-structural strategies is an easy way for applicants and municipal officials to confirm a stormwater management plan meets the standards. Remember that none of these strategies is optional. So for any no responses, only engineering, environmental, or safety reasons should be accepted. Second objective for the applicant developer is to focus on systems that address water quality and groundwater recharge. Non-point source or NPS pollution is pollution associated with stormwater runoff. NPS occurs when runoff collects pollutants on its way to a collection system or water body. NPS pollution cannot be traced to a direct discharge point, such as a wastewater treatment facility. Groundwater recharge requires healthy soils, vertical separation from seasonable high water table or groundwater table, and suitable distance from foundations, basements, and septic systems. Non-point source pollution is a serious factor in water quality. Here are a number of common examples: oil and grease from cars, fertilizers, animal waste, grass clippings, septic systems, sewage leaks, household cleaning products, litter, agriculture, and sediment. The impacts of non-point source pollution can be widespread, from fish and wildlife to recreational water activities, commercial fishing, tourism, and drinking water quality. When complying with the groundwater recharge standard, the infiltration system has to be located so that water does not seep into structures, and the bottom of the system has to be above the seasonal high water table to ensure infiltration. Look at how beautiful and diverse successful bioretention systems and rain gardens can look. Different BMPs result in different TSS removal rates. Remember, combining practices may be necessary to achieve the 80% threshold required. 90% removal would include bioretention systems, constructed stormwater wetlands, or wet ponds. 80% might be achieved with an infiltration structure, a sand filter, or a vegetative filter strip. An extended detention basin may provide 60% TSS removal rates. Manufactured treatment devices, or MTDs, can be used to remove TSS from stormwater runoff, but these systems must first be verified by NJCAT, or New Jersey Corporation of Advanced Technology, and second, certified by NJDEP. These systems that have been verified and certified can be found on this website. The third objective is to design systems that reduce peak stormwater runoff rates and meet water quantity requirements. This involves the calculation of peak runoff rates. We'll provide guidance for this shortly. We are ready to begin the final segment of the program. We have completed parts 1 and 2, the introduction to stormwater management and regulations and best practices. Let's begin part 3, compliance resources. We have developed 6 documents we believe will assist the applicant developer. The complete set is available here as a downloadable document by clicking on the resources link. When reviewing an applicant's plan for stormwater management, municipal officials will apply 7 tests to assess compliance. Each of these relates to one of the elements of the rules. The tests are designed so that if any of the answers is no, the applicant should be asked to make changes and reapply. We recommend advising applicants make all necessary adjustments or changes included in all 7 tests before resubmitting their application. For simplicity when printing for distribution, we recommend printing these tests on color-coded paper to help distinguish them according to the colors indicated here. The next few slides show the questions associated with the test. This is the first of the requirements tests, non-structural stormwater strategies. The second requirements test is for water quality. The next requirements test is for groundwater recharge requirements. The next requirements test is for general stormwater runoff calculation questions. This requirements test is for water quantity requirements. This requirement test has two parts: structural maintenance requirements on this slide and safety requirements on the following. These final questions address the safety requirements. An applicant can meet the 2004 New Jersey Stormwater Management Rules by incorporating non-structural strategies, addressing water quality and groundwater recharge requirements, ensuring proposed designs meet water quantity requirements. We want to make it easy for municipal officials and applicant developers to comply with the 2004 New Jersey Stormwater Regulations. So how can you integrate these requirements into your processes? Actively publicize this program and make it accessible to your applicants and reviewers. Make sure the downloadable attachments are publicly available to all residents, applicants, review engineers, and officials. Members of the planning and/or zoning boards, as well as any environmental commissions, should be prepared to ask these questions of the township's review engineer and applicant. Understand that these questions outline the minimum requirements as defined by the New Jersey Stormwater Rules.